For the first time, humanity built a telescope powerful enough not just to see distant objects, but to observe the universe as it once was. From a quiet point of gravitational balance far beyond Earth, James Webb unfolded, cooled, and began collecting the faint infrared light left behind by the earliest galaxies. What it revealed was unexpected. When astronomers looked into the universe's first billion years, they anticipated small, disordered systems still in the process of forming. Instead, Webb detected galaxies that already appeared large, structured, and surprisingly mature. The discovery sparked debate. Were these signs that our models of galaxy formation needed revision, or that the early universe was far more efficient than we had imagined? For decades, a framework shaped by dark matter and dark energy has successfully described the cosmos on its largest scales. Now, a new eye on the sky was probing how well that understanding holds when confronted with the universe's earliest light. As so often in science, the discomfort came before clarity. The question raised by James Webb is not whether the universe is broken, but whether we are finally seeing it clearly enough to understand how complex it was from the very beginning. This moment of uncertainty did not arrive out of nowhere. History shows a clear pattern. Every time humanity builds a new way to see the sky, the universe refuses to behave as expected. Long before space telescopes and segmented mirrors, the night sky already held power over human imagination. For thousands of years, the heavens were thought to be orderly, eternal, and unchanging. The stars were fixed points, the planets divine wanderers, and the cosmos itself a finished design. That illusion endured until a simple device of glass lenses quietly broke it. In the early 17th century, Galileo Galilei turned a telescope toward the sky. The instrument was crude by modern standards, barely more than a tube with lenses, originally intended for navigation and military use. But when Galileo aimed it upward, he saw things no one was supposed to see. Mountains on the moon, moons circling Jupiter, imperfections where perfection was assumed. The heavens were no longer flawless, they were physical. A few decades later, Isaac Newton reshaped not just astronomy, but the rules beneath it. By replacing lenses with a curved mirror, he solved distortions that had plagued earlier telescopes, laying the foundation for the reflective design still used today. Newton's telescope did not dramatically expand the visible universe, but his laws of motion and gravity did something more profound. They stripped the sky of mystery rooted in divinity and replaced it with laws that applied everywhere, to apples and planets alike. As telescopes improved, they gathered more light, and with more light came complexity. The sky revealed not just stars, but faint, cloudy smudges, objects that did not behave like anything astronomers understood. By the middle of the 18th century, a French comet hunter named Charles Messier grew increasingly frustrated by them. He was searching for comets, which drifted across the sky night after night, but these hazy objects stubbornly stayed put. To avoid confusing them with real comets, Messier cataloged them. More than 100 ghostly shapes were logged and largely ignored. Many were assumed to be simple clouds of gas within our own galaxy. Unknown to Messier, some of these objects lay far beyond anything he could imagine. As the 19th century progressed and telescopes grew sharper, structure began to emerge inside these smudges. Some showed spiraling arms, hinting at rotation. By the early 20th century, the implications were impossible to ignore. In 1921, astronomy faced what became known as the Great Debate. Harlow Shapley argued that the Milky Way was the entirety of the universe, vast enough to contain all observed objects. Heber Curtis disagreed, suggesting that the spiral nebulae were separate island universes, scattered far beyond our own galaxy. The debate ended without a clear winner, but the universe would soon decide for them. Only a few years later, Edwin Hubble used the Hooker telescope to measure distances to these spiral objects. What he found changed everything. They were far too distant to belong to the Milky Way. The universe was suddenly much larger than anyone had believed. And worse or better, it was not static. Galaxies were moving away from one another. Space itself was expanding. In the span of a single generation, humanity's cosmic map had been torn apart and redrawn. The universe was no longer eternal and unchanging. It had a history, a beginning, a story. Each leap in observational power brought a similar reckoning. Larger mirrors, clearer images, deeper surveys. Time and again, astronomers believed they were closing in on the final picture, only for the sky to reveal something new and unsettling. Dark matter, dark energy, structures on scales no theory had fully anticipated. By the end of the 20th century, telescopes on Earth had grown to mirrors spanning many meters, and yet Earth itself remained a limitation. The atmosphere shimmered and blurred the view. To see more clearly, humanity had to leave the planet behind. When the Hubble Space Telescope opened its eye in orbit, the universe sharpened overnight. Galaxies bloomed into focus. Deep fields revealed thousands of distant systems packed into tiny patches of sky. Hubble did not just decorate textbooks and posters, it reinforced the belief that cosmology had entered an era of precision. And it was precisely that confidence that James Webb would come to test. This pattern of confidence tested by revelation threads through astronomy's tapestry, each era building on the last like layers of sediment in cosmic strata. Recall the post-Hubble era, when ground-based telescopes like Keck pushed boundaries further, their adaptive optics compensating for atmospheric turbulence to rival orbital clarity. In the 1990s, Keck's deep surveys hinted at dark energy's acceleration, measurements that complemented supernova data, forcing cosmologists to insert lambda into equations, a term Einstein once dismissed as his greatest blunder, now revived as essential. Yet even as precision grew, surprises lurked. The Very Large Arrays radio maps in the 1980s uncovered jets from active galactic nuclei, plasma streams ejected at near-light speeds, revealing black holes as dynamic sculptors rather than passive pits. Imagine standing under New Mexico's clear skies, antennas arrayed like giant ears, listening to the universe's radio symphony, decoding signals from quasars that Webb now images in infrared detail. Going further back, consider William Herschel's 18th century discoveries. With his sister Caroline, he cataloged thousands of nebulae using handmade telescopes, their mirrors polished by hand in marathon sessions. Herschel's star gauges attempted to map the Milky Way's shape, assuming it was the universe's entirety, a view shattered by Hubble. Yet Herschel's work foreshadowed Webb's. Both sought to count and classify the faint pushing instruments to limits where assumptions crumble. These historical echoes resonate in Webb's data. Just as Galileo's moons of Jupiter upended geocentric models, Webb's exoplanet atmospheres challenge habitability notions. In one case, a planet with a composition that defies explanation, perhaps a carbon-rich world where diamonds form in the clouds, stirs imaginings of alien chemistries born from early stellar forges. Drifting through such visions, we see the continuum. Each tool refines our place in the cosmos, from divine spheres to a vast, evolving expanse. The Planck satellite, Webb's predecessor in mapping the microwave background, exemplifies this. Its 2013 release of the Cosmic Microwave Background Map, with anisotropies measured to exquisite detail, confirmed inflation's predictions while hinting at tensions in Hubble constant measurements, a crisis that Webb helps resolve through Cepheid variable calibrations. Planck's cold vigil, orbiting at L2 like Webb, underscores the site's gravitational serenity, a stable vantage for peering into time's depths. In this lineage, Webb stands as heir, its segmented mirror a nod to Newton's reflectors, its infrared focus an evolution from Jansky's radio hiss. The surprises it delivers, mature galaxies, runaway black holes, aren't endpoints but invitations to deeper inquiry, much as Curtis and Shapley's great debate paved for Hubble's expansion proof. As we ponder what Webb really saw, we honor this tradition. The universe, ever elusive, rewards the patient observer with glimpses of its profound narrative. If James Webb was built to test the details of galaxy formation, another spacecraft had already done something even more audacious. It had attempted to map the universe itself. In the year 2009, a satellite named Planck was launched into space. Unlike Webb, it carried no ambition to image stars, nebulae, or galaxies. Its mission was quieter, colder, and in some ways more abstract. Planck was designed to observe the entire sky at microwave wavelengths, searching not for objects, but for a faint, uniform glow that fills all of space. This glow is known as the cosmic microwave background. It is the after-image of creation itself, the oldest light we can ever observe. Discovered by accident in the 1960s, the cosmic microwave background is the leftover radiation from a time when the universe was hot, dense, and opaque. In those early moments, matter and light were locked together in a plasma so thick that photons could not travel freely. Space was filled with energy, but no light could escape. As the universe expanded and cooled, there came a moment when electrons finally bound to atomic nuclei, forming the first neutral atoms. Suddenly, light was free to move. Photons streamed outward in every direction, carrying with them a snapshot of the universe at that instant. Over billions of years, as space stretched, that light was redshifted from visible wavelengths down into the microwave. Bam! Today it bathes the cosmos at a temperature of just under 3 degrees above absolute zero. At first glance, this background radiation appears almost perfectly smooth. Wherever astronomers point their instruments, they measure nearly the same temperature. But nearly is the key word. With sufficient sensitivity, tiny variations emerge, differences of about 1 part in 10,000. These minute ripples are among the most important structures in the universe. Planck was built to measure them with unprecedented precision. For more than 3 years, it scanned the sky, cooling itself to a fraction of a degree above absolute zero to avoid contaminating its own data. In doing so, it produced the most detailed map ever made of the universe's earliest light. And hidden within that map was a profound revelation. Those faint temperature variations correspond to slight differences in density in the infant universe. Regions that were ever so slightly denser than average would, over time, exert a stronger gravitational pull. Matter would drift toward them, gas would accumulate, and eventually these tiny irregularities would grow into stars, galaxies, and clusters of galaxies. In other words, the entire cosmic structure we see today, every spiral galaxy, every massive cluster, every filament of the cosmic web, can be traced back to patterns imprinted when the universe was still less than a second old. To understand where these ripples came from, astronomers had to go even further back, far beyond the first atoms, beyond the formation of particles, back to a period when the universe underwent a violent and dramatic transformation. This episode is known as cosmic inflation. According to modern theory, in the earliest fraction of a second after the universe came into existence, space itself expanded at an extraordinary rate. Distances that were once subatomic were stretched to astronomical scales. This sudden expansion smoothed out the large-scale geometry of the cosmos, explaining why the universe appears so flat and uniform today. But inflation did something else. At the smallest scales, quantum mechanics dominates reality. Energy fluctuates constantly, appearing and disappearing according to the uncertainty principle. Under normal circumstances, these fluctuations cancel out almost instantly. But inflation disrupted that balance. As space expanded rapidly, quantum fluctuations were frozen in place, stretched from microscopic disturbances into macroscopic features embedded in the fabric of space-time. When inflation ended, its immense energy was released back into the universe, flooding space with matter and radiation. The universe emerged hot, expanding, and filled with particles, but no longer perfectly smooth. Those tiny quantum ripples had become the seeds of all future structure. From that moment on, gravity took over. As the universe continued to cool, protons and neutrons formed. Within minutes, the first simple atomic nuclei emerged. After that, nuclear reactions ceased, and the universe entered a long, dark era. For tens of millions of years, there were no stars, no galaxies, no visible light at all. Yet the darkness was not empty. Invisible matter, dark matter, was already at work. Unlike ordinary gas, dark matter does not collide, cool, or radiate. It responds almost entirely to gravity. In the early universe, it began to flow into the overdense regions seeded by inflation, forming vast halos of unseen mass. Ordinary matter followed more slowly. Gas fell into these gravitational wells, heating, colliding, and eventually cooling. When conditions were right, roughly 100 million years after the beginning, gas clouds fragmented and collapsed. Their cores grew hotter and denser until nuclear fusion ignited. The first stars were born. They were unlike any stars that exist today. Composed almost entirely of hydrogen and helium, many were extraordinarily massive, dozens or even hundreds of times the mass of the Sun. They burned fiercely and briefly, living only a few million years before dying in catastrophic supernovae. But in their short lives, they transformed the universe. Their intense radiation tore electrons from surrounding atoms, ionizing vast regions of space. Their explosive deaths forged heavier elements and scattered them into the cosmos. For the first time, the universe was enriched with the raw materials needed to form planets, chemistry, and eventually life. As stars clustered together, the first galaxies began to take shape. This process was not neat or uniform. Some early galaxies grew rapidly, fed by abundant gas and deep gravitational wells. Others were fragile. A single massive star could expel all their gas in a supernova, extinguishing star formation almost as soon as it began. Many such failed galaxies likely still exist today. Dark, starless halos drifting unseen through space. Over time, gravity continued its slow, relentless work. Galaxies merged. Structures grew. The cosmic web emerged, threading matter into filaments and clusters on the largest scales imaginable. Within these filaments, the early universe's legacy persists in subtle ways, visible through Webb's lens as connections between past and present. Take the supermassive black holes that anchor many galaxies. Their rapid formation in the first billion years puzzles theorists, yet recent detections offer clues. One such beast, confirmed rocketing through space at over 2 million miles per hour, appears ejected from a merger in the cosmic owl galaxies, a pair locked in gravitational embrace, their collision birthing chaos that mirrors primordial mergers. Visualize this runaway giant, trailing a wake of ionized gas like a comet's tail, its path a fossil record of violent youth. Challenging models of how black holes stabilize early structures. This violence extends to exoplanets, worlds that Webb probes for signs of the universe's chemical enrichment. In a striking observation, the telescope captured an exoplanet dramatically shedding its atmosphere, a helium plume evaporating under stellar winds. A real-time glimpse of planetary evolution that echoes the gas loss in fragile early galaxies. Such worlds, stretched by tidal forces or scorched by radiation, reveal how feedback shaped the cosmos. Supernovae and quasars expelling material, only for it to reconvene elsewhere. Pondering these, we see the quantum ripples enduring influence. Inflation's fluctuations, frozen into density variations, not only seeded galaxies but also the voids between immense emptiness where matter is sparse yet traversed by faint gas bridges. Webb's mapping of these voids uncovers hidden quasars, their light red shifted to infrared, illuminating reionization patchy progress. Like ink spreading on wet paper, ionization bubbled outward, clearing paths for light to travel unimpeded. The first stars, those population 3 behemoths, played pivotal roles here. Composed of pure primordial elements, they fused helium into heavier nuclei in their cores, only to explode and disperse them. Webb's spectra detect these signatures in distant gas clouds, traces of carbon and oxygen that hint at life-enabling chemistry emerging early. Imagine a star 100 suns massive, its core collapsing in a hypernova, shock waves rippling through the web, compressing gas into new nurseries. Black holes, too, weave into this narrative. The Virgil anomaly, a massive hole masquerading as a quiet galaxy, suggests seeding mechanisms where direct collapse in overdense regions birth giants swiftly. This bypasses slow growth, allowing quasars to flare soon after the Dark Ages, their radiation ionizing vast swaths. Feedback from these, winds and jets, regulated galaxy growth, preventing runaway star formation, a balance that Webb observes in action through lensed images, gravity magnifying distant scenes like a cosmic loop. Extending to our solar system, Webb's view of trans-Neptunian objects reveals pristine surfaces, relics from the protoplanetary disk 4.5 billion years ago, echoes of the gas-rich environments in early galaxies. A newly spotted moon around Uranus, tiny and elusive, adds to this local archive, its orbit a miniature of galactic dynamics. Similarly, the interstellar comet 3I Atlas, streaking through with alien ices, carries compositions from beyond, linking interstellar chemistry to primordial gas clouds. In this interconnected view, Webb's observations of the beginning aren't isolated. They resonate through time, from inflation's quantum whispers to today's exoplanet atmospheres. The early universe's efficiency, rapid mergers, swift enrichment, explains the mature galaxies, not as paradoxes but as inevitable fruits of a fertile cosmos. As gravity continues its work, the Webb tightens, structures sharpen, and Webb stands as witness, unraveling the threads one spectrum at a time. And this brings us back to James Webb, because when Webb looks into the early universe, it is peering into this formative era when galaxies were just beginning to assemble, when theory predicts they should still be small, chaotic, and immature. Yet some appear otherwise. The question is not whether our cosmological framework is broken, and by 2025 those surprises keep unfolding, like soft waves rippling across a cosmic lake. JWST has confirmed the first runaway supermassive black hole, a colossal beast hurtling through the paired galaxies known as the Cosmic Owl at 2.2 million miles per hour, as if ejected from its home after a violent merger. This forces astronomers to rethink how black holes form and migrate in the young universe. Or consider the earliest supernova detected, GRB 250314A in December, a brilliant explosion that lit up when the universe was just 730 million years old, illuminating secrets about the deaths of the very first stars. These youthful galaxies, with their seemingly mature structures, are no longer seen as chaotic blobs, but as slender, filamentary threads, like rivers of stars flowing through the void. In surveys like Jade's, they've revealed hints of wave-like dark matter, perhaps axion particles, allowing galaxies to form smoothly along cosmic filaments earlier than expected. What once seemed a threat to our models now whispers of a universe that was simply more adept at weaving complexity from the start. Delving deeper into this whisper, recent observations from Webb illuminate the role of supermassive black holes in this accelerated weaving. Consider the confirmation of an actively growing black hole in a galaxy only 570 million years after the Big Bang, a mere cosmic toddler, yet already hosting a monster at its heart. This black hole, greedily devouring surrounding gas, shines as a quasar, its light piercing through the reionization era when the universe transitioned from opaque fog to transparent clarity. Imagine it as a lighthouse in the primordial dark, its accretion disk spinning at relativistic speeds, converting matter into energy with efficiency that dwarfs nuclear fusion. Such findings challenge the timeline of black hole growth. Traditional models posited slow accumulation from stellar remnants, but Webb suggests alternative paths. Direct collapse from dense gas clouds, bypassing the star phase entirely. In July, data revealed hints of this in high redshift objects, where massive seeds formed rapidly, shaping their host galaxies from the inside out. This interplay, black holes regulating star formation through outflows, while galaxies feed them material, creates a feedback loop that accelerates maturity. What Webb sees isn't anarchy, it's symbiosis, a dance where gravity orchestrates harmony from discord. Extending this to galactic structures, surveys like JD's and Sears uncover filamentary galaxies, slender threads along the cosmic web scaffolding. These aren't isolated islands but connected streams, funneled by dark matter into efficient assembly lines. One recent image captured a pair of dwarf galaxies in a gravitational tango, their interaction birthing new stars in bursts that echo the early universe's productivity. Picture them twirling, arms extended in spiral embrace, gas compressing into luminous knots, precursors to the mature disks that surprised us. This efficiency manifests in unexpected compositions too. Webb's spectra reveal metal-poor environments where star formation ignites faster, unhindered by heavier elements that would otherwise slow cooling. In these pristine conditions, massive stars dominate, their supernovae enriching the cosmos swiftly, seeding subsequent generations with carbon, oxygen, and iron, the stuff of planets and life. The telescope's view backward thus becomes a mirror forward, showing how the universe's youth laid the groundwork for our existence. Yet amid this productivity, anomalies persist. The Virgil object, a shape-shifting black hole hidden in plain sight, forces reconsideration of growth mechanisms in the infant cosmos. Appearing as a quiescent galaxy but harboring immense mass, it suggests periods of dormancy punctuated by feasts, a rhythm that models must now incorporate. Drifting through these revelations, one senses the universe's subtlety. Not a brute force of creation, but a nuanced evolution where small variances amplify into grand designs. To grasp this, reflect on the reionization epoch, when first stars and quasars ionize neutral hydrogen, clearing the fog for light to travel freely. Webb's infrared penetration allows us to map this transition, revealing bubbles of ionized gas expanding like soap films in the void. These bubbles, merging over millions of years, created the transparent universe we inhabit. What seemed a slow process now appears expedited by clustered activity, where early overdensities, those inflation-seeded ripples, concentrated energy, igniting chains of formation. In essence, Webb's gaze at the beginning of time unveils a universe that was always in a hurry, not out of impatience, but because the laws of physics permitted it. Gravity pulled, quantum fluctuations provided the seeds, and dark matter framed the canvas. The mature galaxies aren't outliers. They are the natural outcome of a system optimized for complexity from the start. As data accumulates, models evolve, not shattered, but enriched. Like a story gaining depth with each retelling, it is whether the early universe was more efficient, more dynamic, and more complex than our models had assumed. And that distinction matters, because history suggests that the universe rarely shatters our understanding outright. Instead, it stretches it, forcing us to refine, adjust, and deepen the stories we tell about where everything came from. By the beginning of the 21st century, cosmology had reached a rare moment of confidence. After generations of debate, revision, and uncertainty, astronomers believed they finally understood the large-scale behavior of the universe. Not in every detail, but in its broad structure, how it began, what it contains, and how it evolves over time. This framework became known as the lambda cold dark matter model. At its heart were two invisible ingredients. The first was dark matter. Long before James Webb ever opened its mirrors, astronomers had realized that the visible universe could not account for the motions they observed. Galaxies rotated too quickly. Clusters of galaxies held together too tightly. Something unseen was adding extra gravity, matter that did not shine, absorb, or emit light, yet outweighed all stars and gas combined. The second ingredient was even stranger. In the late 1990s, two independent teams set out to measure how cosmic expansion had changed over time. They used a specific type of exploding star, type Ia supernovae, as cosmic mile markers. These explosions shine with nearly uniform brightness, allowing astronomers to infer distances across billions of light years. The expectation was clear. Gravity, produced by all the matter in the universe, should be slowing cosmic expansion. Instead, the data revealed the opposite. The expansion of space was accelerating. To explain this, cosmologists introduced a new component: dark energy. Unlike matter, it does not pull inward. It pushes outward, acting uniformly throughout space. In Einstein's equations, it appears as a term known as lambda. When astronomers added everything together, the picture was startling. Ordinary matter, the atoms that make up stars, planets, and people, accounted for only a small fraction of the cosmic budget. Dark matter made up much more, but dark energy dominated all. And yet, with these ingredients in place, the universe suddenly made sense. The lambda cold dark matter model explained the cosmic microwave background, the growth of structure, the expansion history of the universe, and the distribution of galaxies on the largest scales. It predicted a universe approximately 13.8 billion years old. It allowed astronomers to translate redshift into time, to look at distant objects and know how old the universe was when their light began its journey. This was precision cosmology, And it is precisely this precision that made the first results from James Webb so unsettling. Because according to this model, galaxies in the first billion years of cosmic history should be small and irregular. They should still be assembling, fed by slow streams of gas and gradual mergers of smaller systems. Massive, well-defined disk galaxies were expected to be rare, if they existed at all. Yet Webb appeared to find them. Headlines followed quickly. Phrases like cosmology in crisis spread beyond academic journals into mainstream media. One research paper famously opened with the phrase, "panic at the disks," capturing the shock that structured, rotating galaxies seemed to appear far earlier than expected. For some, this sounded like a death sentence for the standard model of the universe. But beneath the headlines, cosmologists were more cautious, because there is a crucial distinction in modern astronomy, one that often gets lost outside the field. The lambda cold dark matter model describes the universe on the largest scales. It governs how space expands, how matter clusters overall, and how the cosmic web forms. What it does not describe in detail is how gas behaves inside individual galaxies. Galaxy formation is messy. It depends on turbulence, cooling, radiation, magnetic fields, supernova explosions, and the growth of black holes. Many of these processes occur on scales far too small to simulate directly across the entire universe. Instead, astronomers use approximations, recipes that encode complex physics into manageable rules. These recipes are powerful, but they are not sacred. James Webb was not challenging the foundations of cosmology so much as it was stress testing the assumptions buried inside galaxy models. One of those assumptions concerns something known as the stellar initial mass function. This function describes how many stars of different masses are formed when a cloud of gas collapses. In the nearby universe, it follows a fairly consistent pattern. Many small stars, fewer large ones, and very few extremely massive stars. But this distribution is measured locally in a universe that is already old, metal-rich, and evolved. The early universe was none of those things. If the first generations of galaxies produced proportionally more massive stars than expected, they would shine far more brightly than modern galaxies of the same mass. Webb would then see them as larger and more mature than they truly were. The apparent contradiction would soften, not because the universe was wrong, but because our assumptions were incomplete. There are other uncertainties as well. Gas may have cooled faster, star formation may have been more efficient. Mergers may have occurred earlier and more violently than models predicted. Black holes may have grown rapidly, shaping their host galaxies sooner than expected. Each of these adjustments remains comfortably within the boundaries of the larger cosmological framework, and slowly, as more data arrived, the initial panic began to fade. The galaxies Webb had observed were still surprising, but no longer impossible. What emerged instead was a familiar pattern, not the collapse of an idea, but its refinement. The realization that the early universe was more active, more chaotic, and more productive than previously imagined. In that sense, James Webb was doing exactly what it was built to do, not to confirm our expectations, but to confront them. By the time the first galaxies began to assemble, the universe had already undergone several dramatic transformations. It had expanded, cooled, and emerged from its earliest darkness. But what followed was not a calm settling into order. It was an era of intensity. The early universe was a place of excess. Gas was abundant, gravity was efficient, and the processes that govern star formation operated at a pace far faster than anything seen today. In young galaxies, vast clouds of hydrogen and helium collapsed rapidly, fragmenting into stars at extraordinary rates. Many of these stars were massive, short-lived, and unstable, burning through their nuclear fuel in only a few million years. Their deaths were not quiet. Supernova explosions tore through surrounding gas, injecting enormous amounts of energy into their host galaxies. Shock waves compressed nearby material, sometimes triggering further star formation, while at other times blowing gas completely out of shallow gravitational wells. In the smallest galaxies, a single supernova could effectively end star formation altogether, leaving behind dark halos stripped of the raw material needed to make new stars. But stars were not the only engines shaping this young universe. At the centers of many forming galaxies, gravity funneled gas inward. As material spiraled toward the core, it heated up, flattened into disks, and accelerated to extreme velocities. In some cases, this infalling matter fed compact objects whose influence would come to dominate their surroundings. Black holes. Unlike stars, black holes do not shine by themselves. But when gas falls toward them, friction and compression convert gravitational energy into radiation with astonishing efficiency. The result is one of the most luminous phenomena in the cosmos. These objects became known as quasars. In the early universe, quasars were far more common than they are today. Many are observed at distances so great that their light has traveled for more than 10 billion years to reach us. This means that supermassive black holes, some containing masses billions of times that of the Sun, were already in place when the universe was less than 1 billion years old. This presents a fundamental challenge. Growing a black hole to such a size requires both time and a steady supply of matter. Yet the early universe seems to have accomplished this rapidly and repeatedly. How these black holes formed so early, whether from the collapse of massive first-generation stars or from direct collapse of dense gas clouds, remains an open question. What is clear is that their influence was immense. Quasars did not simply light up the universe, they reshaped it. Their radiation heated surrounding gas, regulated star formation, and altered the evolution of entire galaxies. In some cases, they may have shut down further growth by expelling gas entirely. In others, they may have triggered bursts of star formation by compressing material at the edges of their influence. This violent interplay between stars, gas, and black holes defined the character of the early cosmos. And yet, for all this activity, none of it was visible to the first generations of astronomers. Because this story is not written only in starlight. Up to this point, everything humanity knew about the universe came from one source, light that the human eye could, at least in principle, see. Stars, planets, nebulae, and galaxies revealed themselves through visible wavelengths. Telescopes grew larger, mirrors wider, images sharper, but they all remained bound to the same narrow window of the electromagnetic spectrum. The universe was assumed to speak primarily in light. That assumption was wrong. In the early 1930s, an engineer named Carl Jansky was not searching for galaxies or cosmic origins. He was working for Bell Laboratories, tasked with a practical problem of the modern age: improving long-distance radio communication. His job was to identify sources of interference that disrupted transatlantic radio signals. What he encountered made no immediate sense. A persistent hiss appeared in his data, rising and falling with a steady rhythm. At first, Jansky suspected local thunderstorms, industrial noise, or equipment malfunction, but the signal refused to behave like any terrestrial source. Day after day, it returned with almost mechanical regularity. The key clue emerged only after careful, patient observation. The interference did not repeat every 24 hours, the length of a solar day. Instead, it followed the sidereal day, repeating roughly 4 minutes earlier each night. This subtle drift meant the signal was not tied to the sun, nor to Earth itself. It was fixed relative to the stars. The conclusion was unavoidable. The source of the noise lay far beyond the solar system, deep in the heavens. Space itself was emitting radio waves. With this realization, a new universe quietly came into existence, one that had always been there, but had never been perceived. Jansky had opened the door to radio astronomy. At the time, his discovery attracted surprisingly little attention. Radio waves were invisible, abstract, and difficult to reconcile with the familiar beauty of optical astronomy. Jansky himself was reassigned to other work, and the field might have stalled entirely had it not been for one determined individual. In the late 1930s, an amateur astronomer named Grote Reber built the first purpose-made radio telescope in his backyard. Working largely alone, he constructed a large parabolic dish and began systematically scanning the sky. His equipment was crude by modern standards, but the results were unmistakable. The Milky Way glowed, not faintly, not sporadically, But consistently, our galaxy was a powerful source of radio emission. This was not reflected starlight, but radiation produced by energetic processes within interstellar space. The universe, it turned out, was active in ways no optical telescope could reveal. As radio surveys expanded after the Second World War, the sky grew stranger still. Astronomers began detecting intense radio sources scattered seemingly at random across the heavens. These sources were extraordinarily powerful, yet appeared point-like, tiny in angular size. When optical telescopes were directed toward their locations, many looked like ordinary stars, or revealed nothing obvious at all. They were named quasi-stellar radio sources, quasars. The name itself reflected confusion. These objects looked like stars, but behaved like nothing known. Their radio output was immense, dwarfing that of entire galaxies. When their spectra were finally measured, the mystery deepened. The light from quasars was profoundly redshifted, indicating that they lay at enormous distances. They were not nearby curiosities, they were ancient. Quasars were visible from across more than 10 billion years of cosmic history, meaning they were already shining when the universe was very young. To produce that level of energy from such a compact region required a radical explanation, one that would have been unthinkable only decades earlier. Supermassive black holes. At the centers of quasars sit black holes containing masses millions to billions of times that of the Sun. As gas falls toward these objects, it forms a rapidly spinning disk, heating to extreme temperatures and radiating across the electromagnetic spectrum. The efficiency of this process is staggering, far greater than nuclear fusion. For the first time, astronomers were confronted with evidence that black holes were not rare or passive. They were central players in cosmic evolution, shaping galaxies from their cores outward. This realization transformed the story of the early universe. The young cosmos was not merely forming stars and assembling galaxies at a steady pace. It was punctuated by phases of extreme activity, bursts of radiation powerful enough to influence regions far beyond individual galaxies. Quasars heated intergalactic gas, regulated star formation, and carved out vast ionized regions in space. And crucially, they revealed that much of the universe's most important activity was invisible to the eye. Light alone was not enough. Radio astronomy had shown that to understand cosmic history, astronomers would need to observe the universe across the entire electromagnetic spectrum. Infrared, ultraviolet, X-rays, microwaves, each would uncover processes hidden from the others. This realization would reshape telescope design, observation strategies, and theoretical models for decades to come. And it set the stage for something even more profound. Because once astronomers accepted that invisible radiation could reveal unseen structures, a new question emerged. If radio waves could expose hidden violence in the universe, what might the faintest, oldest radiation of all reveal about its very beginning? To answer that, astronomers would have to stop looking at individual objects altogether and instead map the sky itself. Once astronomers accepted that much of the universe was invisible to the eye, their attention began to shift away from individual objects and toward something far larger, the universe itself. Radio astronomy had revealed violence. Optical telescopes had revealed beauty. But neither, on their own, could explain how matter was arranged on the grandest scales. Galaxies were not scattered randomly across space. Even in early surveys, patterns were beginning to emerge, hints that the universe possessed an underlying structure. At first, these hints were subtle. Galaxy counts showed regions rich with galaxies and others strangely empty. Clusters appeared where gravity had gathered thousands of galaxies into tight associations. Between them stretched vast, sparsely populated expanses that seemed almost devoid of matter. These were not observational gaps. They were real. As surveys grew deeper and more complete, the picture sharpened. The universe was not a uniform fog of galaxies. It was a network. Astronomers began to describe this architecture as the cosmic web. Galaxies traced out immense filaments and sheets, stretching across millions of light years, intersecting at dense nodes where galaxy clusters formed. Between these filaments lay enormous voids, regions where matter had been drained away by gravity, leaving behind near emptiness on scales that dwarf entire galaxy groups. This structure did not arise by chance. Its origin can be traced back to the same tiny fluctuations imprinted in the cosmic microwave background. Regions that were slightly denser than average exerted a stronger gravitational pull. Over billions of years, matter flowed along invisible gradients, streaming out of underdense regions and into growing filaments and clusters. Dark matter played the central role. Because it does not collide or radiate, dark matter began clumping first. Its gravity sculpted the large-scale framework of the universe, creating the scaffolding upon which ordinary matter later accumulated. Gas fell into these dark matter wells, cooling and condensing to form galaxies along the filaments of the web. In this sense, galaxies are not the primary structure of the universe. They are decorations, luminous tracers outlining a much larger, darker skeleton. At the intersections of the cosmic web lie galaxy clusters, some of the most massive objects ever to form. These clusters can contain thousands of galaxies bound together by gravity, embedded in halos of dark matter that outweigh all visible matter combined. Within them, galaxies move at tremendous speeds, sloshing through hot X-ray emitting gas that fills the cluster environment. Clusters themselves are not isolated. They group together into even larger associations known as superclusters, regions spanning hundreds of millions of light years. These are not neatly bounded objects, but sprawling concentrations of mass whose gravitational coherence is still debated. Our own galaxy resides within one such region, part of a vast basin of attraction known as Laniakea. From this perspective, the Milky Way is not a solitary island drifting through space. It is a participant in a slow, gravitational migration, moving through the cosmic web toward denser regions over unimaginable spans of time. But structure is not static. As matter flows along filaments and into clusters, galaxies inevitably encounter one another. Gravity bends their paths, draws them together, and sometimes forces them into close interaction. When this happens, the results can be dramatic. Galaxies distort each other's shapes. Tidal forces stretch out long streams of stars. Gas clouds collide and compress, triggering bursts of star formation. In some cases, galaxies merge entirely, forming larger systems with new morphologies and altered futures. These interactions are not rare accidents. They are a fundamental mechanism of galaxy evolution. Over cosmic time, small galaxies are consumed by larger ones. Disks are disrupted. Spins are altered or erased. Spiral galaxies can be transformed into massive ellipticals through repeated mergers. The diversity of galaxy shapes observed today, spiral, elliptical, irregular, is a record of this long history of interaction. What appears at first glance to be a quiet universe is anything but. Even now, galaxies continue to drift, collide, and grow. The cosmic web channels matter inward, feeding the densest regions and slowly emptying the voids. Structure becomes more pronounced, not less, as time passes. And this process has not finished. The Milky Way itself is still growing. Evidence of this became unmistakable toward the end of the 20th century, when astronomers began to find signs that our galaxy was not merely interacting with its neighbors, but actively consuming them. To understand how this was discovered and what it reveals about our place in the universe, we must narrow our focus once again. Away from the vast cosmic web, away from clusters and superclusters, back to our own galaxy, and to a small, faint system hidden in plain sight. By the late 20th century, astronomers had grown accustomed to the idea that galaxies evolve through interaction. Theoretical models predicted mergers, accretion, and slow growth driven by gravity. But theory alone was never enough. What was missing was direct, unambiguous evidence that such processes were still happening in our own cosmic neighborhood, not billions of light years away, but here and now. That evidence arrived quietly through the motion of stars. In the early 1990s, a young graduate student named Rodrigo Ibada was studying stellar motions near the center of the Milky Way. His goal was straightforward: to understand how stars move within the galactic bulge, the dense central region of our galaxy. To do this, he relied on observations made with the Anglo-Australian telescope, located far from Cambridge. beneath the clear southern skies of Australia. The telescope's instrumentation allowed astronomers to measure the velocities and chemical compositions of many stars at once, turning individual points of light into dynamic tracers of galactic structure. When Ibata began analyzing the data, most of what he saw matched expectations. Stars in the bulge moved on complex orbits, their motions shaped by the deep gravitational potential of the Milky Way. But in certain regions of the sky, something did not fit. A group of stars appeared to be moving together, sharing a common velocity pattern that made little sense if they belonged to the galactic bulge itself. At first, the most likely explanation seemed mundane: measurement error, instrumental bias, statistical coincidence. Astronomers are trained to distrust surprising results, and Ibata was no exception. But as the analysis deepened and alternative explanations were ruled out, the anomaly remained. These stars were not native to the Milky Way. Together with his supervisors, Ibata reached a radical conclusion. The stars he was observing were remnants of another galaxy, one that was in the process of being torn apart by our own. This system became known as the Sagittarius Dwarf Galaxy, a small, faint companion of the Milky Way that had gone unnoticed for centuries because its stars were spread thinly across a vast area of sky. Unlike distant dwarf galaxies, which often appear as smooth, compact smudges of light, Sagittarius was ragged and elongated. Its distorted shape was not subtle. It was the unmistakable signature of tidal disruption. As it orbited the Milky Way, gravitational forces stretched it apart, pulling streams of stars from its core and wrapping them around our galaxy like cosmic debris. This was not a past event inferred from simulations or distant observations. It was happening now. Further studies revealed long stellar streams arcing across the sky, the fossil remains of Sagittarius's repeated passages through the Milky Way's disk. Each orbit stripped away more material. Each close encounter fed our galaxy with stars, gas, and dark matter. In a few billion years, Sagittarius would cease to exist as a distinct object, its remains fully absorbed into the Milky Way's halo. The implications were profound. Sagittarius was not unique. Once astronomers knew what to look for, similar structures began to appear. Other stellar streams were identified, evidence of additional dwarf galaxies that had already been consumed. The Milky Way, long thought of as a stable, mature system, was revealed to be actively growing, still assembling itself through the slow consumption of smaller companions. This process became known as galactic cannibalism. Far from being an exotic or rare phenomenon, galactic cannibalism emerged as a central mechanism of galaxy evolution. Large galaxies grow not only by forming new stars from gas, but by absorbing the stars of smaller systems. Over time, these mergers alter a galaxy's structure, chemistry, and dynamics. They thicken disks, populate halos, and seed complex stellar populations, whose origins can be traced through motion and composition, and the Milky Way is no exception. Our galaxy's stellar halo is now understood to be a mosaic built from the remains of multiple accreted systems. Each stream of stars carries a memory of its former home, encoded in its orbit and elemental makeup. By reading these signatures, astronomers can reconstruct the Milky Way's history, not as a single isolated object, but as a product of countless interactions spanning billions of years. Seen in this light, the calm appearance of the night sky is deeply misleading. Galaxies are not static islands drifting peacefully through space. They are dynamic systems shaped by gravity, collision, and continual transformation. Even now, as the universe ages and star formation slows, the long work of assembly continues. And this realization changes how we interpret the distant universe. If the Milky Way is still growing through mergers today, then the early universe, denser, richer in gas, and more crowded, must have been even more violent. Interactions that take billions of years now could have unfolded far more rapidly in the past. Galaxies could assemble mass, structure, and complexity faster than simple models once assumed. This context matters, because when James Webb observes surprisingly mature galaxies in the early universe, it is not witnessing an impossibility. It is catching a process in mid-motion, one that we can see continuing in our own galaxy, scaled up across cosmic time. To understand those distant observations, we must therefore understand ourselves. The Milky Way is not a finished product. It is a living system shaped by the same forces that govern the universe from its earliest days. And in its ongoing growth, it offers a nearby tangible example of how galaxies truly evolve. Once the Milky Way was revealed to be an active participant in galactic cannibalism, the idea of a finished, settled galaxy quietly collapsed. What had once seemed like a stable spiral disk floating serenely through space was now understood as a structure still under construction, shaped by forces that began billions of years ago and have never truly stopped. Our galaxy does not exist alone. It resides within a small association known as the local group, a gravitationally bound collection of galaxies dominated by two large spirals, the Milky Way and Andromeda. Around them swarm dozens of smaller systems, dwarf galaxies of various sizes, many faint enough to have escaped detection until deep surveys of the last few decades. These dwarfs are not merely companions, they are future fuel. The local group is a dynamic environment. Galaxies drift within it on long, slow orbits dictated by gravity and dark matter. Over time, those paths intersect. Smaller systems are stretched, stripped, and ultimately absorbed. Larger ones grow ever more massive, their halos expanding as they gather stars and dark matter from their surroundings. The Milky Way's future is already written into this structure. Andromeda is approaching. Careful measurements of stellar motions and galactic velocities show that the two largest members of the local group are moving toward one another. In several billion years, they will collide, not as solid objects crashing, but as immense gravitational systems interpenetrating and merging. Their disks will distort, their stars flung into vast arcs, their gas clouds compressed and heated. Over time, the remnants will settle into a single larger galaxy, likely elliptical in form. This future merger is not exceptional. It is the natural outcome of structure formation in the universe. From the smallest dwarf galaxies to the largest cluster center giants, growth through merger is the rule, not the exception. Each interaction leaves behind signatures, stellar streams, chemical gradients, altered dynamics that persist long after the visible drama has faded. The universe is filled with these records, waiting to be decoded. Seen this way, the Milky Way becomes a laboratory. By studying its structure in detail, its halo, its streams, its satellite galaxies, astronomers can reconstruct a timeline of past mergers and interactions. Each accreted system adds a chapter to the galaxy story, a fragment of the broader cosmic narrative encoded in motion and composition. This perspective reshapes how astronomers interpret the distant universe. When telescopes observe galaxies billions of light years away, they are not seeing static snapshots. They are seeing moments within a continuous process. The early universe was denser. Galaxies were closer together. Gas was more abundant. Under those conditions, interactions that now take billions of years could unfold far more rapidly. Young galaxies could grow quickly, not slowly assembling over cosmic ages, but building mass through repeated mergers in efficient star formation. Disks could appear earlier. Structure could emerge sooner. What once seemed too mature may simply reflect a universe that was more efficient at building complexity than previously assumed. This is where the local and the distant connect. The same processes shaping the Milky Way today, accretion, merger, cannibalism, were operating in the early universe, only amplified by higher densities and greater energy. The difference is not one of kind, but of scale and pace. And this continuity matters deeply when interpreting the observations made by James Webb. Because Webb does not observe galaxies in isolation. It sees them embedded within a universe already structured by dark matter, already shaped by gravitational flows, already primed for rapid growth. The early galaxies it detects are not anomalies floating outside theory. They are expressions of processes that can be studied directly nearby in our own galactic neighborhood. The lesson is subtle, but powerful. The universe does not evolve in neat stages, cleanly separated from one another. The mechanisms that govern galaxy growth do not switch on and off. They operate continuously from the first billion years after the beginning to the present day. James Webb is not revealing a universe that contradicts this story. It is revealing one that demands we take it seriously in all its complexity. And to understand what Webb truly sees when it looks back toward the first galaxies, we must now return to the instrument itself, to the assumptions it tests, the expectations it confronts, and the deeper meaning of the surprises it has delivered. Because the question is no longer whether galaxies can grow quickly. The question is how well we have understood the universe's capacity for growth all along. By the time the first images from James Webb began circulating, the universe they depicted felt uncomfortably familiar. Not because astronomers had seen it before, but because it resembled something they believed should not yet exist. Galaxies appeared structured, extended, and in some cases disk-like, at a time when theory suggested such order should still be rare. The instinctive reaction was to look upward, to the foundations of cosmology itself, and ask whether something fundamental had gone wrong. But this instinct, powerful as it is, misunderstands what James Webb was built to test. Webb does not primarily test the expansion of space, the age of the universe, or the presence of dark matter and dark energy. Those pillars of cosmology are constrained by measurements that operate on the largest possible scales: the cosmic microwave background, baryon acoustic oscillations, large-scale structure surveys. Webb enters the story much later, in a different regime entirely. It tests how galaxies turn theory into reality. At the heart of this lies a critical distinction. Cosmology describes the stage on which the universe evolves. Galaxy formation describes the actors moving across it. The stage set by the lambda cold dark matter model determines how matter clusters overall and how space expands. But what happens inside individual galaxies depends on processes far more intricate, far less settled, and far more difficult to model. Gas does not behave politely. It cools, heats, shocks, fragments, collapses, and responds to radiation in nonlinear ways. Stars form in bursts, not at steady rates. Massive stars explode, injecting energy back into their surroundings. Black holes grow, flare, and sometimes regulate the very galaxies that feed them. Each of these processes operates across vastly different scales, from the interiors of stars to regions spanning thousands of light years. No computer simulation can resolve all of this directly. Instead, astronomers rely on approximations, subgrid physics, empirical recipes, and assumptions calibrated using the nearby universe. These models are remarkably successful, but they are also provisional. They work because they capture the average behavior of galaxies over long periods, not because they encode every detail correctly. James Webb forces these assumptions into the open. One of the most important is the stellar initial mass function. This function governs how many stars of different masses form when a cloud of gas collapses. In the modern universe, it is dominated by low-mass stars, with only a small fraction of massive luminous ones. This distribution shapes how bright a galaxy appears for a given amount of mass. But the early universe was not modern. It lacked heavy elements, its gas cooled differently, its star-forming environments were more extreme. Under such conditions, the stellar initial mass function may have been skewed toward higher mass stars. If so, early galaxies would shine far more brightly than their mass alone would suggest, making them appear larger, older, and more developed than they truly were. This single adjustment has enormous consequences. A galaxy that looks massive in light may be far less massive in stars. Structure that appears mature may be transient. Disk-like features may be short-lived configurations rather than stable systems. What Webb observes in this view is not a contradiction, but a translation problem, interpreting unfamiliar conditions using familiar assumptions. There are other assumptions under strain as well. Star formation efficiency may have been higher in the early universe. Gas accretion along cosmic filaments may have delivered material more rapidly. Mergers may have occurred earlier and more frequently than models predicted. Black holes may have grown faster, influencing their host galaxies sooner and more strongly. None of these possibilities require abandoning the cosmological framework. They require refining the physics of galaxies. This distinction is subtle, but crucial. The lambda cold dark matter model does not predict the detailed appearance of individual galaxies. It predicts the statistical environment in which they form. Webb's observations operate precisely where uncertainty is greatest, not at the level of the universe as a whole, but at the level where gravity, gas, radiation, and feedback collide. In this sense, the headlines declaring a crisis in cosmology miss the deeper point. James Webb is not exposing a broken universe. It is exposing the limits of our simplifications. This exposure of limits invites a broader contemplation. If Webb reshapes our view of the early universe, what does it imply for the cosmos's future? Synergies with upcoming telescopes, like the Nancy Grace Roman, promise wider fields to complement Webb's depth, mapping billions more galaxies to refine dark energy's equation. Yet even now, Webb stirs dreams of life beyond, revisiting worlds like K2-18b, where hints of biosignatures linger in hazy atmospheres, molecules that could echo the chemistry forged in those first supernovae. Consider the resilience Webb uncovers. Exoplanets defying erosion, their compositions a puzzle of unexpected elements, perhaps remnants of metal-poor stars. These worlds, lava-covered or diamond-raining, expand our imagination of habitability, linking back to the efficient complexity Webb sees at time's dawn. The universe, it seems, was primed for diversity from the start, its laws allowing myriad forms to emerge. In this light, the crisis headlines fade into perspective. Webb doesn't herald collapse, it catalyzes growth, urging adjustments in subgrid physics, those approximations modeling turbulence and feedback on unresolved scales. As simulations incorporate Webb's data, predictions sharpen, early mergers more frequent, star formation bursts more intense, black holes seeding sooner. The Lambda model stands firm, its large-scale predictions intact, while galaxy recipes evolve, like a chef refining ingredients for a timeless dish. Drifting through these refinements, one feels the universe's patience. From the cosmic microwave background's smooth glow to the Webb's intricate filaments, simplicity begets richness. Webb at L2's equilibrium embodies this, balanced in gravity's dance, cooling in silence to capture warmth from eons past. Its discoveries, like the runaway black hole or evaporating atmospheres, are threads in an ongoing weave, each surprise a knot strengthening the fabric. Ultimately, what James Webb really saw at the beginning of time is not a fixed origin, but a vibrant genesis, a universe bursting with potential, where quantum seeds blossomed into galactic gardens faster than we dared dream. This vision humbles us, reminding that our models are maps, not territories, ever subject to revision as new horizons unfold. As stars wheel overhead and photons arrive from afar, Webb continues the conversation, one deeper question at a time, inviting us to listen, learn, and wonder anew. As we look ahead, JWST's gaze promises even more layers to uncover, perhaps in synergy with future missions like the Nancy Grace Roman Telescope, which will map billions of galaxies with wider eyes. In April 2025, JWST revisited K2-18b, a potential ocean world detecting hints of dimethyl sulfide, a molecule linked to life on Earth, stirring quiet dreams of biology beyond our shores. These glimpses don't demand revolution. They invite nuance, urging us to adjust our stellar initial mass functions or rethink gas cooling in metal-poor eras, all within the sturdy frame of our cosmological model. The universe, in its patient expansion, teaches humility. What we see as maturity in those ancient galaxies may be the bloom of efficiency, where mergers and feedback loops wove order from turmoil sooner than anticipated. And so, as night falls and stars emerge, remember that JWST isn't closing the book on the cosmos, it's merely turning the page, revealing that reality's richness lies not in final answers, but in the endless invitation to wonder, one faint photon at a time. This has happened before. Each major leap in observational capability has forced astronomers to confront the gap between idealized models and messy reality. Galileo did not overthrow celestial mechanics, he complicated it. Hubble did not destroy astronomy, he expanded it. Radio telescopes did not invalidate optical astronomy, they revealed what it had been blind to. James Webb belongs to this lineage. It was never meant to confirm what we already believed. It was designed to push observation into regimes where confidence gives way to revision. The early universe, as revealed by Webb, is not gentler or simpler than expected. It is more efficient, more active, and more productive than our initial models allowed. And this realization carries weight beyond galaxies alone. Because the way galaxies form determines how elements are produced, how radiation reshapes space, and how conditions for future planetary systems emerge. Understanding early galaxy formation is not a niche concern. It is a foundational chapter in the story of cosmic evolution. What Webb is really testing, then, is not whether our universe exists as we think it does. It is whether we have been bold enough in our imagination of how quickly complexity can arise when gravity, matter, and time are given free rein. And to answer that question fully, we must now step back one final time to place James Webb itself into the long arc of scientific discovery, and to ask what it means when the universe answers us with surprises rather than certainties. James Webb was never designed to give comfortable answers. It was designed to extend the long tradition of astronomy in which every improvement in vision reveals not clarity, but complexity. From Galileo's first glimpse of imperfect heavens to Hubble's discovery of an expanding cosmos, each new eye on the sky has forced humanity to revise not only what it knows, but how confident it feels about knowing it. In that sense, the reaction to Webb's earliest images follows a familiar pattern. Surprise is mistaken for contradiction. Tension is mistaken for collapse. Headlines rush to declare the end of understanding when history suggests the opposite. What Webb revealed in the early universe was not a violation of physical law, but a reminder of how efficient the universe can be when conditions allow. Galaxies did not politely wait to mature. They formed in an environment dense with matter, threaded by dark matter filaments, flooded with gas, and shaped by gravity acting on every scale at once. Under those conditions, growth was rapid. Star formation was intense. Mergers were frequent. Black holes ignited early and powerfully. Complexity did not creep into existence. It emerged explosively. This does not undermine the cosmological framework painstakingly built over the last century. The expansion of space still follows the same laws. The cosmic microwave background still encodes the same primordial patterns. Dark matter still sculpts structure on the largest scales. Dark energy still drives the universe apart. What changes is our appreciation of how much can happen inside that framework. The universe has never been a simple place governed by simple outcomes. It is governed by simple laws, applied relentlessly across vast scales of time and space. From that repetition emerges richness. From that persistence emerges structure. From that patience emerges surprise. James Webb sits precisely at this intersection. It does not rewrite the universe's origin story. It fills in the missing chapters. It shows that the early universe was not a quiet prologue to cosmic history, but one of its most productive and transformative eras. The galaxies Webb observes are not anomalies to be explained away. They are evidence that the universe was already hard at work, building the foundations of everything that would follow. And in doing so, Webb reframes a deeper question. Not whether our theories are fragile, but whether our expectations were too modest. Astronomy advances not by closing questions, but by sharpening them. Each answer carries within it the seed of the next uncertainty. This is not a weakness of science. It is its defining strength, the willingness to revise, to refine, and to accept that the universe will always be slightly ahead of our understanding. Seen from this long view, James Webb is not a crisis. It is a continuation of a conversation that began when humans first looked upward and wondered what lay beyond the lights of the night sky. A continuation of the realization that reality is always richer than intuition suggests, and a continuation of the truth that progress in knowledge rarely arrives as confirmation, but as challenge. Somewhere beyond the reach of any spacecraft, the earliest galaxies continue to fade into darkness as their light stretches and thins across an expanding universe. That light carries no intent, no message, only information. James Webb receives it without judgment. What we choose to do with it, how carefully we interpret it, how humbly we revise our models, and how patiently we expand our understanding will determine not whether our cosmology survives, but how well it grows. Because the universe has never promised to be simple, only to be discoverable, one deeper question at a time. The light James Webb collects does not arrive all at once. It comes gradually, patiently, one faint signal at a time. And so does understanding. What we have explored here is only a small part of a much larger picture, one that continues to evolve with every new observation. There are more galaxies to trace, more worlds to revisit, and more questions waiting quietly beyond the horizon. This is a good place to stop for now. If you'd like to return to these questions in future episodes, consider following the channel. New videos continue this slow exploration of space, time, and the hidden structure of the cosmos. Until then, the universe keeps its silence, and the next chapter will be here when you're ready.